Yeah, I'm fine, everyone. Start off. Great. So last thing that we did was this one. Great. Now, let's just brief up everything that we did. So if you have a resistance R, it just behaves like a resistance. So the phasor form will be R and the phase angle is 0. Hope everyone has gone through the entire notes once. Stuff is easy if you understand, or else it can look confusing. This we write it as XL, which is XL is J omega L. Remember, when they give it in the books and all, they will never put this J. It is something which we have created. The XL bar is your phasor form, magnitude omega L, and J is 90 degrees. This is XC, so XC is minus J by omega L. XC bar is 1 by omega C minus 90 degrees. So these are called reactances of inductance and reactance of capacitance. Now, if you combine all this, if you have a combination of all this stuff, we'll get complex number. This is called impedance. Z, which is R plus JX. R is your resistance of a circuit. X is the reactance of the circuit. This is called impedance. So instead of saying R equivalent, we will call it impedance, which is a combination of both resistance and reactance. Mod Z will be root over R square plus X square. So, if it's a complex number, you can treat this thing as R. Someone said something? Ivan, you got something? Okay. This is X and this is your impedance Z and this is your phase angle phi. So tan phi will be X by R. Yeah, this is the thing. So you can write the phasor angle Z bar as mod Z phase angle phi. Clear with this? This is what you had done last time. Then if I give you V is equal to V naught sine omega t plus phi, we know the phasor form of this thing will be the amplitude V naught and angle phi, where V naught is your peak value, phi is your phase angle. Let's call it as alpha because we're already using phi for the X by Z. Now for convenience, if I take V is equal to V naught sine omega t, the phasor angle will be V naught 0. So from here we will get current I bar is V bar by Z bar, which will be V naught by Z, angle will be minus phi. That means current as function of time t can be written as V naught by Z sine omega t minus phi. So this here is your I peak. If I divide by root 2 on both the sides, this will become I RMS is equal to V RMS by Z. So if you just want RMS values, right? For example, if you want VR RMS, it is simply I RMS into R. Basically, you don't need any angles or anything. You can just multiply. If you want voltage across the capacitance RMS value, then it is simply I RMS into XC. VL into RMS will be I RMS into XL and so on. So if you just want RMS values, you can just use V is equal to IR. Generally, that is a type of question they'll ask you at mains and bits. Clear with this? Next thing, great. So we know how to find the current, we know how to find the voltage, blah, 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 everything. Then if there's a current and voltage, then you also have power. Now remember, power, the formula is pretty straightforward. It doesn't matter what kind of device you have, power is simply voltage into current. In case of resistance, V into I, V also became IR, so it became I square R. That is a special case. For a capacitance, it is voltage across the capacitance into current in the capacitance. For a battery, it is voltage across the battery into current in the battery, and so on. So same way here, it is V naught sine omega t, that is a voltage. And current will be I naught sine omega t minus phi, which we derived just now, sine omega t minus phi. So this is your some basic one. Multiplying, you end up with V naught, I naught. And that will be sine omega t and sine omega t minus phi. This looks like sine A, sine B, which can be written as V naught, I naught by 2, cos A minus B. That's cos phi minus cos 2 omega t plus phi. This would be your instantaneous power. So the battery is providing this power as function of time t. And you can clearly see your frequency is 2 omega. That means power oscillates with a frequency of 2f. We have seen something similar in SHM, do you remember? The frequency of oscillation is f, then the energy will have a frequency 2f. Because it's a sine square function, periodicity becomes half. So here power, this is the mains question. So when you say the frequency in the house is 50 hertz, it's actually oscillating 100 times per second. But you know, if something is oscillating 50, 100 times per second, instantaneous doesn't make sense. So we take average. So average will be integral p dt. This will be V naught I naught by 2t. Remember, phi is a constant. And for a cos function in one time period, you get 0. It doesn't matter what function you take. A cos per one cycle will always give you a 0. This becomes 0. So you end up with V naught I naught cos phi t by 2t. You got V naught I naught by 2 cos phi. That's your average power. Clear with this? So let me put this in a more usable form. Next thing. So the average power E naught I naught cos phi by 2. Remember, these are peak values. Huh? Me naught and I naught are peak values. So if I write this thing as V naught by root 2, I naught by root 2, they become RMS values. And we can also write what is VRMS? IRMS into Z. That's a definition of IRMS if you remember. IRMS of the system will be nothing but VRMS by R equivalent. We don't call it R equivalent, we call it Z. So this is one formula here. Power average is VRMS. IRMS cos phi. So you can write IRMS as VRMS square by Z. So that will be VRMS square by Z cos phi. This is another way of writing. But the one that I like is you can replace VRMS with IRMS into Z. That will be I square RMS Z cos phi. And we have here cos phi is nothing but R by Z. This is called power factor. Another important formula. This will become IRMS square into R. The normal formula which you know, isn't it? I square R. That's the best thing. So it looks like your DC ka formula. It will be easy to remember I square R. So what is this power factor exactly? This power factor cos phi, we prefer it to be as close as possible to 1. Let's talk about that a bit. So generally the value is around 0.9. The meaning of this is for 100 watts of power supplied, you can only actually use 90 watts. Why is that? The thing is, have a look at this page. Let's see. So what is the meaning of this power factor exactly? Now, if you look at this, see, when you have a circuit, resistor, inductor, capacitor, and everything, let's assume you have a very perfect circuit without any resistance. So this resistor would be generally the device in your house, maybe the bulb or the fan or AC or whatever it is. So every wire, right, has an inductor and a capacitance. So when you're making the coil, see, what is your motor exactly? A motor is nothing but a lot of windings. If you ever, did you ever see a fan guy inside? If you ever see the fan inside, right, you have 3 coils like this and you have a lot of copper windings. They're supposed to generate magnetic field. Now, in return, what will happen? The moment you create a solenoid, you have created an inductance even without realizing it. A wire is also has some kind of capacitance. So every system has inductance, every system has capacitance and resistance. Now, the problem is this. Generally, it is not a problem. Think about it. When I give some energy, inductors and capacitors store some energy. So technically, you're not losing any energy. So if you switch off the circuit, right, and if you switch on the circuit again, technically you should recover this energy back. But in real life, what happens? These inductors and capacitors themselves have some internal resistance. So when you switch it on and switch it off, the energy gets dissipated internally. So these energies you cannot recover. Let me give an example like this. In Alaska, right, they found a big petroleum deposit on the north side. Right now, they wanted to transport this fuel down south. Now the problem is, the Russia is there is the Bering Strait. So a ship going like this and collecting the oil and coming back, there's a lot of icebergs and it's pretty dangerous. So what these people did, they built a pipeline. I think it's roughly around 800 kilometers, I guess. 800 or 180, 200 something. It's a pretty big one, more than 200 kilometers. Right? Now you tell me, the moment I start generating oil here and start pumping, do you think the fuel will come out immediately? It takes around 5 days. It takes around 5 days for the fuel to come. That means at any point of time, when you pump the fuel in the first day, first of all, you have to fill up this pipe, isn't it? First, the pipe has to be filled up, only then the fuel comes out. That means even when I switch off the pipeline here and switch off the pipeline here, at any point of time, there is enough fuel in the pipe itself that you can fill up 1 or 2 ships. You're getting it? So technically, second time when you switch it on, what will happen? Do you need to fill the entire pipe again? No, right? So you have to do it only once and the fuel is there always. But imagine this pipe has small, small holes. So every time you switch it off, what will happen? That all that oil will leak. So next time again, you have to fill it up. Kind of making sense? So our situation is like that only. Even though the inductor and capacitors are not supposed to dissipate energy, because of their own internal resistance, they mess up the whole energy part. So we get the power factor. So if your power factor is 1, that means circuit becomes purely resistive. Whatever. So we get more efficiency that way. So when you say power factor cos phi 1, matlab you're saying phase angle is 0. That means this formula tan phi, which is R by X by R, X becomes 0. That means if you can create a circuit where XL and XC both are equal, that means L and C, whatever energy is being provided, it just distributes between them. Something happens, right? You will get a perfect circuit where there is no dissipation. So yeah, end of the day, the story is that. So the thing is, tell me one thing, if the company is supplying 100 watts and you can use only 90 watts, how much bill are you going to pay for? 100 or 90? You have to pay for 100, right? The company will say, it is not my problem. I generated 100, I want money for 100. You can't go and argue like I used only 90, so I'll pay for 90. The 10 watt is a transmission losses. You can't do anything. Unfortunately, this transmission losses are not happening only because of the wire, but your inductor and capacitor also messing up. Technically, which they shouldn't have been doing it in the first place, but can't avoid it. So generally, the power factor in your house is around 0.91, 0.9. So 10% of the power is always gone. So that is the simple story about power factor. Now, long back, almost I think a decade back, I went to a certain exhibition or workshop or something, and there I saw a guy and I had a stall and he's selling some devices, which looks like वो होता है ना mosquito का killing वाला device. What is that thing? It looked like that, but a bigger version. And this guy was telling everyone this. Use this in your house. If you put this in your house and put a plug and switch it on, your power bill, power bill will reduce. You will get 10-15% efficiency. This is what he was telling and selling everyone. And I was thinking, like, what the hell is this guy talking about? Matlab, if you take this box and see, this is what, nothing to do, huh? Just take this box in your house, any plug point, put it there and switch it on. Automatically your power bill reduces. This is what he was saying. I thought, yeah, ये तो कुछ fraud होगा. I didn't understand. I ignored it. Then after 6 or 7 months, I saw some guy in the train also selling this. Literally, you know, train में they sell. Na, this guy is selling. Now that was pretty clear. ये तो fraud है. But it never clicked what happened. Then one day, I think after a few years, one day I was coming out of the gym. I was wearing my shoes and some guy was talking. Sir, we will install a capacitor room in your factory. इससे power factor बढ़ जाएगा. Then we can save money. For some reason, it hit me suddenly. Like, okay, I said, okay, shit. Then I started tying my, shoelaces thoda slowly to hear what he was talking. And I was listening. So this is the conversation that was going on between him and some owner. He said, like, sir, we will install a capacitor room in your factory. It will cost around 25 lakhs. Right? And your power factor will improve to something 0.6 से 0.7, 0.72 हो जाएगा. Every year you will save some 10 to 12 lakhs. Within 2-3 years, you will recover the money. This is what he said. This much I understood. And from there, I inferred the remaining information. So what happens in a factory, right? Your regular power supply is 0.9 power factor. But in a factory where you use a lot of machines and everything, there are huge coils. That means you have a huge self-inductance. So in a factory, the capacitances are very small, but inductances are huge. Now your formula XL minus XC, whatever you have, the L will start dominating. They're not equal. So because of this, what happens in a factory when the power receives, the power factor becomes around 0.6. Some factories even have 0.5. They lose a lot of energy in this inductance only. So what this guy was suggesting is we will build a room full of capacitors and we will keep this room in series to your factory circuit. Thereby, we will improve your capacitance of the system and your power factor will go from 0.6 to 0.7 or 0.75. This will give you an efficiency of around 8 to 10% more. Now, the thing is in a factory, right, your electricity bill goes to almost 10 to 15 lakhs per month, depending on how big the factory is. And you can save 10% of 10 lakhs every month. That is 1 lakh per month. In a year, you're saving almost 12 lakhs. And it costs them 25 lakhs to build it. Within 2 years, they'll recover anything. So the concept was right. The guy who was selling in the train and the guy who was selling in the exhibition, what they said, if you put the box in the house, it works. The concept is right, but they're bluffing big time. The problem was this. Everyone, right, was saying you'll get 10% efficiency, 15% efficiency. Arey God, you already have 0.9 power factor. If you get 15% efficiency, you'll get 1.05. You will generate power out of nothing then. You're getting the problem. Maximum, that 0.9 will become 0.901 or something. The problem was the claim. Your electricity efficiency increases, but it will increase by 0.5% or 0.2%, which is not worth. The problem was the tactic of selling that you will save 2 to 3,000 every month. The problem was that. So a device actually works. So you can use the device, especially you can put a capacitors in a room where you have a factories, especially where you have a huge inductance. So generally in your house, our house, nothing much happens. If you put a big capacitor, you can still take it to 0.95, but it is not worth. Anyway, so that is a bit about the capacitor and the power factor thing. Next thing. So we can combination of elements, but it took me almost 2 years to figure out what the hell they're talking about. I saw everything. I just remember there is a guy who was selling a box. I didn't figure out what it was. 2-3 years later in a gym, someone is talking and for some reason it strikes. Happens a lot. I'm pretty sure when you're solving questions also happens a lot. You don't get it anything on that day. Next day you're doing something and suddenly it clicks. Oh shit, I should have done like that. Ever happened? Happens a lot. Series. So if you have two impedances, now I'll not put a resistor symbol. I'll just put some rectangular boxes, Z1 and Z2. You can replace them with one impedance, Z equivalent. So Z equivalent will be Z1 plus Z2. Just like series resistors and everything. Example. Z1 is 1 plus j, and Z2 is 2 plus 3j. You can just add them. Z equivalent will be add the real parts, add the imaginary parts. 3 plus 4j. Regular complex numbers, nothing new. If you have circuits in parallel. You can replace this with 1. 1 by Z equivalent is 1 by Z1 plus 1 by Z2. The only thing, be careful when you're adding and subtracting, it's all complex number operations. Let's say this is 1 plus j. This is 2 minus 2j. The Z equivalent will be 1 plus j, 2 minus 2j, 1 plus j, 2 minus 2j. Take out 2 common, that will become 1 minus j square by 3 minus j. That will become 4 multiply 3 plus j by 9 minus j square. That would be 4 by 10, 3 plus j. I factorized it. What will be the magnitude? So if you write the phasor form Z equivalent, that is 4 by 10 root 10. So that's 4 by root 10. And phase angle is phi, where tan phi is 1 by 3. Clear with this? Regular complex numbers, once you get the final complex number, you can put it in a phasor form. Any doubts on this? Next thing, Wheatstone bridge. Like I said, everything works. That's the best part about the phasors. Once you convert that into a phasor form, you can use all your DC stuff. So there's no need to invent any new thing. But then again, whatever I'm teaching you at a mains level is kind of too much actually. You don't need this much. But advanced level, the problems they get, there you will get trapped. The regular stuff which you see in the book, yeah, you can handle with that, but I found it boring. It's confusing also. There, same stuff, Ij is equal to 0. That means Z1 by Z2 must be equal to Z3 by Z4. So you can do Z1, Z4 is equal to Z2, Z3. That means the real terms of Z1, Z4 must be equal to real terms of Z2, Z3. The imaginary of Z1, Z4 is imaginary of. If this is satisfied, the current will be 0. Next thing. Let's see some questions on this. So there we have everything there. We will see the basic stuff also. We will see those kind of questions also. Because going about this way will actually take more time if you do those easy questions. But these are the advanced questions. So this XC is announced. Like I said, they'll never give you the complex number. They'll simply say XC. R is ohms, XL is 10 ohms, and let's say this is 100 root 2 volt. Now look at this thing here, the problem. They'll say 100 root 2 volt. And look at the symbol. That symbol is an AC ka symbol. And you're giving 100 root 2. Can an AC voltage be constant? No, but you gave me this. So what does this mean? This is an RMS value. Always keep that in mind. In the exam also, they will say voltage across the resistance is this, and answers are 10, 20, 30, 40. Now, in an AC circuit, voltage should change with time, but you're saying you're giving constant options. He's asking about RMS values. Clear? So if they just mention it like this, right, this must be an RMS value. And how do you need to sort a DC circuit? Look at the symbol. There's an AC ka symbol. If you actually wanted to say DC, then your symbol should have been like this, na? Then I'll assume it is a DC battery. You gave me a round symbol and you're telling me constant. So for an AC source, if a constant value is given, it is an RMS value. Same thing. If they ask you to find the current in the branch, look at the options. If they're giving us function of time t, fine. But if they're giving numbers, they're asking RMS values. So this is I, this is I1, this is I2. Find I as function of time t. I1 as function of time t, I2 as function of time t, voltage across the resistance as function of time t, average power factor. There, let's get them. Try. I'll give you 3, 4 minutes. This is a big one. Let's see. Keep doing. Anyways, I'll keep showing one after another. So let's convert everything into complex numbers. So this guy is minus 10j. So this voltage is actually, remember, this is the RMS value. The V peak is actually 200. So if you write everything in the phasor form, this is Z1, which is 10 minus 10j. Z2 is 10j. So Z1 bar is 10 root 2 minus 45. Z2 bar is 1090. V bar is 200, 0. This is I1 and this is I2. So I1 bar is voltage by Z1, they're in parallel. So V bar is 200, that is 10, that's 20 by root 2, 10 root 2. 45 degrees. I2 bar will be again V bar by Z2 bar. That's 20 minus 90. So I1 is function of time t. Now, if they're asking for RMS value, you know what to do. This is the peak value by root 2. Sin omega t plus 40, I2 is function of time t. 20 sin omega t minus 90. What else you want? You want VR of t. VR bar will be the current is I1 bar into R bar. That will be 10 root 2, 45. And R bar will be 10, 0. 100 root 2, 45. This is the voltage across the resistance as function of time t. Any doubts still here? Wouldn't be 20 into 90. V2 by Z2, na? When 90 goes up, it becomes minus, right? V by Z2. It should be 20. No, V1 by Z1 is how much? Z1 is 10 root 2, na? Or am I getting confused somewhere? The I1 is V1 by Z1. Z1 is 10 root 2. Z2 is 10.
No, in the question, we've taken I1 and I2 ulta. That's why
Ah.
I didn't notice. Sorry.
नहीं मेरा मिस्टेक था. ठीक है, चेंज कर लेते हैं ना. नहीं, what you're saying is right. ठीक है. I took I1, I2 up and down. Then fine, we got the same thing. Any doubts still here? Now, once we got this, how do you find current I? Remember, I told you as long as it is in phasors, you can just directly add them. So we got I1 bar 10 root 2, 45. I2 bar 2090. So the current I bar is I1 bar plus I2 bar. You can directly add them. But how do you add two phasors? You just can't add the numbers. Do you guys remember this? I taught you how to add complex numbers. Is that? Complex number operation. This is what we do normally. There is another way to do this. I'll show that also, but let's see this thing. So 10 root 2, 45. So 10 root 2, 45 degrees with the reference line. I'll take reference as always horizontal. That is 20 minus 90 degrees. So 20 in 90 degrees. So I need to find the resultant of these two. So that will be 10 root 2 cos 45, 10, 10. That means this is your I bar and 45 degrees. Therefore, I bar is 10 root 2 minus 45. Is that making sense? And we know voltage V bar will be 200, 0 degrees. So you can clearly see this is your phase angle. Isn't it? So yeah, you're done. So what do you want to find? Power will be VRMS, IRMS cos phi. So VRMS will be, this is 200 by root 2, 10 root 2 by root 2, and that's cos 45. Root 2 goes off, 1 by root 2, this will be 100 watts. What is the power factor? Cos phi. One by root 2. You get everything from here. If they ask you for Z equivalent, I can find that also. Z bar, remember these are peak values. So I can even find Z also. Z can be written as V peak by I peak or VRMS by IRMS, same thing. That would be 200 by 100, 10 root 2. That is the equivalent resistance of the circuit magnitude. Clear with this? There is another way to do. If they're just asking you for the power factor, right? They don't want all this current and everything. The faster way to do is find the Z equivalent. Let me show you that also. So Z1 will be 10 minus 10J. Z2 will be 10J. So Z equivalent will be Z1, Z2 by Z1 plus Z2. That would be 10 into 1 minus J, 10J, 10. 10 cancels. We get J minus J square. 1 plus J. So Z equivalent will be 10 root 2. Phase angle 45 degrees. There we got the same magnitudes here. And this is your, so what do you want to find? You want to find the main current I. So I bar will be V bar by Z equivalent bar. That would be 200 by 10 root 2 minus 45. 10 root 2 minus 45. You got the same? This is faster. You can just find Z equivalent and finish it off. But if they ask you current in each branch, then you have to do that, what we did before. And then once you got this, you got everything actually. This is the phase angle, na phi. Power factor aa jayega. You get everything. From here you'll get IRMS. So you can. So in this thing, there are two parts. See. So this Z, which we got 10 plus 10J, this is the equivalent circuit R, and this is the X of the circuit. So you can replace this entire thing with a resistor of 10 ohms and 10J. Don't get confused with this 10. Luckily, we got the same number. It's not necessary to get the same number. Coincidentally, it came out like that. That 10 has nothing to do with this 10. If I had given some other numbers, you won't get 10 here, you'll get something else. Clear how we handle this? Any doubts on this? So there is a alternate way. You can just find the whole Z equivalent and solve.
Will the potential along the R of the resultant Z be the same as VR as a function of time?
नहीं ना, कुछ है ही नहीं relation.
This
are, like I said, this R and that R are not same. No, when you replace this whole thing, you can the whole thing you can treat it as one resistor 10. Current is not same na, in that 10 and this thing. Clear with this? Let's see one more like this. I think if you got that, then I think you got this. I think if you understood this problem right, you know you'll be able to handle a lot of problems. In advanced, you won't have a problem. This is an advanced problem. 2012, I guess. This was a PYQ. I'm not sure when they asked, but I think it's 2012. They asked bits and pieces of it. It became a subjective question. Let's get this. Mains में general, they'll never touch parallel circuits. Little rare, they can touch, but not this kind of extensive things. This looks scary, but yeah, manageable. Get this, you got 4-5 minutes. Try. Let's see. Step 1, let's convert everything into resistances. 4, and this is 3J. This is 6, and this is 8J. And this is 10 minus 10J. 10J minus 10J. And again, that is your RMS value. So V bar is 100 root 2, 0 degrees. So Z1 bar is 4 plus 3J, that is 5. 3 by 4 is 37 degrees. Z2 bar is 10, 53 degrees. Z3 bar is actually 10, 0. Is that clear what I did? Let the currents be I1, let the current be I2, let the current be I3. So I1 bar will be 100 by root 2 by 5. 20 root 2 minus 37. I2 bar will be 100 root 2 by 10. 10 root 2 minus 53. I think I goofed up something. This is minus 8J. So this is minus 53. So this is 53. So I3 bar is 10 root 2, 0 degrees. Then I got current in each branch. You want as function of time t, you know how to write that as function of time t. I1 at time t is 20 root 2 sin omega t minus 37. I2 of 2, 10 root 2 sin omega t plus 53. There. You want that power in the PR1? That you need I1 square RMS into R1. Remember, those are peak values, which is 20 square into R1 is 4. 1600 watts. Please ask me if you're confused. I'm skipping a lot of steps. I'm not writing simplified each and every term. This is I2 RMS square into R2. So if you want a power in a particular resistance, just take IRMS square in that resistance into R will give you the answer. Then what is I2 ka RMS? 10 root 2, so 10 square, and the resistance is 6 ohms. 600 watts. PR3 will be I3 square RMS into R3. That is 10 square into 10, that's 1000 watts. This is the power in each resistor. So what's the total power? Total power is 3200 watts. And then we finished current, we finished power, and you have to find the net current and the impedance of the circuit. Net current is this guy. Let's find I bar and the impedance of the circuit. Now, impedance of the circuit, actually you can find R equivalent and do that, or the other way around. I'll show you with the currents. I think if you take 1 by R equivalent, that will be 1 by Z1 plus 1 by Z2 plus 1 by Z3, no? I don't think it look that, it doesn't look that great. I'm not sure though. We need to multiply all that and get Z equivalent in the form of A plus BJ types. Let's get the current, everyone. Solve. How do you find I bar? I bar is what? I1 bar plus I2 bar plus I3 bar. Phasors. Let's get that. I'll give you a minute or two. I know Z looks bad. Let's see what is the current. So I1 bar is 20 root 2 minus 37. Ten root 2 53. Ten root 2 0. I bar is I1 bar plus I2 bar plus I3 bar. And how do you add phasors? Just like vectors. So 20 root 2 minus 37, you take this as a reference. And that's 10 root 2 53. This is 10 root 2 0. So if I can add these three vectors, my job's done. And they don't look that great. So vertical direction, horizontal will get 10 root 2 plus 10 root 2 cos 53 plus 20 root 2 cos 37. Vertical direction 20 root 2 sin 37 minus 10 root 2 cos 53. How much is this? Take out 10 root 2 common, 1 plus 5 to 8 by 5, 7, 12, 12 by 5, 5 to 24 root 2. That would be 10, that's 12 plus 3 by 5 plus. 11 by 5, 11 plus 16, 16 to 32 root 2. How much is this guy? Take out 10 root 2 common, 6 by 5 minus 3 by 5. Six root 2, no, that's 4 by 5. Where I go for something, this is sin 53. It's going to be 4 root. Then the result of these two, that will be your I, and this will be your phase angle. So I will be, what is our magnitude again? Shit, 4 root 2 square, that will be 32 plus 32 square into 2, take out 132 common, 65, 32 into 65. 130, 0, 8, 2080 is angle 5. And tan 5 will be 4 root 2 by 32 root 2, 1 by 8. There, that's your current as function of time t. And what is IRMS? I think I forgot there's a root here. IRMS will be 2080 by 2, root 1040. What do you want to find? Impedance? Z is nothing but VRMS by IRMS. VRMS is 100. IRMS is root 1040. That's your impedance. Clear with this? Yeah, I think Om got it. 4 root 130. I think, yeah, you guys got it. Check it out. It's a little lengthy, but mathematics part is a little lengthy, but overall, that's it. That's how you add phasors. Clear with this? There, if you can handle this, I think you got everything. You'll get whatever you want. One power factor cos phi, you know phi. Another way to do this thing is get all these things. I don't know how good is that. That will be 1 plus 4 3j plus 1 by 6 minus 8j plus 1 by 10. If you do the operation, you'll get this equivalent. Then you take z equivalent. I think even that will take the same amount of work. Anyway, that is one. Clear with this? Take a break. Come back by 9:45. We'll continue from here. Any doubt so far? Great. Chalo, let's start off. Now let's see the regular stuff. Now in our portion, technically mains and all, we have only RLC series circuit. Straightforward circuit. Resistance, inductance, and a capacitor. By now, you know already how to handle this thing. But there are other things I wanted to show you. Let's say this is V naught sine omega t. So if you try to write Kirchhoff's law, you will get V naught sine omega t minus IR minus LTA by dt minus Q by C is equal to 0. If you differentiate this with respect to time, this will become V naught cos omega t. This will become R di by dt. L d square I by dt square minus I by C is equal to 0. If you rearrange the terms a bit, so this is the equation. Let's say if you have a spring block system, and let's say someone is applying a force F is equal to F naught cos omega t. Again, just a comparison. And let's say there is an air resistance also present. Spring constant is K, and let's say there is an air resistance. Basically, this is a forced oscillations, which is also not removed from the mains portion damped oscillations. F is equal to minus BV bar. So if you try to draw the FBD of this block, because these things can be in advanced paragraph, they'll explain something like this and they'll ask you a question based on oscillations. F naught cos omega t, let's say velocity v is this way, acceleration a is this way, then we have the spring force kx backward, then we also have air resistance backward. Now if you try to write this equation, F naught cos omega t minus kx minus bv is equal to ma. Arrange the terms and see, you will notice that will be m d square x by dt square plus b dx by dt plus kx is equal to F naught cos omega t. Can you see the resemblance? So here current ka place mein what you have elongation, right? They will ask you that question, find the elongation of the spring as function of time t. So what am I asking you indirectly here? Find the current in the branch as function of time t. Don't you know how to solve that? So we can find the current from there and then we can say the same as the elongation in the spring. Like I said, as long as the mathematical equations look similar, Max doesn't care. We can't solve this problem normally. And see, not one thing, it is pretty messed up. What we studied in SHM was what? There was no air resistance. There was no external force. We only studied MA is equal to minus KX, isn't it? So if you introduce two weird things, an air resistance and a variable force, it becomes pretty complex to solve. But if you can compare this with an RLC series circuit, suddenly the current in the circuit looks like spring elongation in the spring. So they can ask you find the displacement of the block as function of time t. Clear with this? Anyway, so that is just a comparison in case if at all they try to do something, you can play with this thing. These are called forced oscillations. Anyways, so next thing, so how do we solve the circuit? You already know this stuff. But the thing is, in the books, you will not see all that complex number and all that thing that we did. So here we know the impedance is R plus J into X, where X is nothing but XL minus XC. So impedance will be root over R square omega L minus 1 by omega C whole square. There. So in all the books, you'll find that. And what is impedance? Root over R square plus omega L minus 1 by omega C whole square. But remember, this is only for series. We did for any other weird circuit, we know how to handle them. But for series circuit, this is the formula. Similarly, this thing will be XL minus XC by R. Again, remember, this is only valid for series. All you need to do is put one more, if I just put one resistor like this, the whole thing is gone. We got tan phi from there. Current I is V naught by Z sine omega t minus phi. This also we derived it, which comes from I by V Z bar. Cos phi is the power factor. Power is VRMS, IRMS, cos phi. Put it on. Yeah, you can write more. This can be also written as IRMS square into Z. Same stuff. Clear? Next thing. Now, we also know how to find this VR as function of time t and everything. Just let me write it down that also. VR bar is I into R bar. That will be V naught by Z into R sine omega t minus phi. This will be V naught by Z omega L sine omega t minus phi plus 90. That is minus 90. So there are a few things here. So V source as function of time t will be voltage across the resistor as function of time t plus voltage of inductor as function of time t, voltage of capacitance as function of time t. But you can't do the same thing for RMS values. You can't say V source RMS. This is not equal to VR RMS plus VL RMS plus VSC RMS. Can you tell me why can't I add the RMS values directly? As function of time, I can add them because from Kirchhoff's law. Again, what is RMS value? Peak by root 2, right? If you're adding all the things, what are you telling? You are saying VR, all these three functions will reach the maximum at the same time. Will that ever happen? This is sine, this is cos. Sine and cos can't go to maximum at the same time. Then how do we add them? Normally, we take current as a reference because all are in series. The voltage and the current are in phase. Inductor is 90 degrees ahead. Capacitance is 90 degrees behind. So if you see the resultant, so when you take RMS values, you can use voltages like vector quantities, basically phasors. So we are comparing everything with this. This will be your V source. This will be your phase angle. So this is the relation between the RMS values. V source RMS will be root over VR RMS square VL minus VC square. So instead of sometimes, right, they'll not give you always resistances, they'll give you voltages. So if they ask you to study in terms of voltages, you can just write this thing as VL minus VC by R. Since current is same, the current series, we use I as reference. So with respect to current, we study everything. Clear with this? There. You can add them as function of time t, but RMS values have to be used using this formula, VL minus VC whole square. So this is basically the phasor form. How did we get that vector form? Look at this. These are phasors. But in the textbook, right, they'll not explain all this stuff. They'll directly put it as perpendiculars and finish it off. And the explanation they'll give is this thing. Remember how I added them? V and I are in the same direction. For an inductor, V and L are perpendicular. For a capacitor, V and L are perpendicular. So they are going to show this vectors and say these are phasors, and they'll finish it off. Clear? Not only that, let's say if you just want RMS values, like mains per general, they want RMS values only. So if you want VR RMS, you can simply take I RMS into R. You can use your Ohm's law. So VL RMS, I RMS into XL. And you might think like, how did we get that voltage ka formula tan phi? VL minus VC by VR. This is actually nothing but if you remove IRMS from here, this is XL minus XC by. Isn't that the same formula? XL minus by XC by R. So if you just multiply IRMS on the top in the denominator, the resistances and impedances suddenly become voltages. Is this clear, everyone? So if whenever they ask you for RMS values, you can just treat them like vectors and finish it off. Yeah, next thing. We still got a bit of a theory. Now, if you look at that current I, which we got it as I naught, which is V naught by Z, which is V naught by root over. Again, all this is for only series circuit. Omega L minus 1 by omega C whole square. That means if you notice something here, the current is actually changing with frequency. So we define something called a resonant frequency. So omega will only mess up that impedance. If omega L minus 1 by omega C becomes 0, we get omega is 1 by root LC. This is called a resonant frequency. So you can actually change the current in the circuit by messing up the frequency without even changing any elements. This is the same thing which we got in LC oscillations. So at this resonant frequency, X of the circuit becomes 0 and Z becomes equal to R. Circuit becomes purely resistive. And Z is minimum. And I is maximum. So if you actually try to plot the graph, I versus omega, this is how it goes. And you reach a peak value here. This is your omega resonance. And not only that, the phase angle phi becomes 0 and power factor becomes 1. Ideally speaking, this is the best case that can happen. But like I said, circuits generally have more inductance than capacitance. Same time, if you want to draw for Z also, if you draw Z versus omega, it kind of looks like this. You'll get Z minimum here. Kind of, it will be inverse of it. Clear this? That means there is one particular frequency where you get a maximum current. This is another important concept, resonant frequency. Next thing. What if the frequency, like I said, every time it won't be resonant frequency. So if XL is greater than XC, omega L greater than 1 by omega C. So we get omega will be greater than 1 by root LC. That means if your frequency is greater than resonant frequency, the circuit becomes inductive. So sometimes they'll ask a question like this: is the circuit inductive or capacitive? Inductive meaning it's dominated by an inductance. Similarly, if XL is less than XC, omega is less than omega resonance. Circuit is capacitive. So if you can't play with the capacitance and inductance, you can mess up with the frequency to get what you want. But again, changing frequency is not that great. Yeah, inductance, it more behaves like an LR circuit. Not only that, if your frequency, if you have high frequencies, if you remember, inductor is j omega L, capacitor is minus j by omega C. So if omega tends to infinity, this value tends to infinity and this value tends to 0. An inductor will become like an open circuit. Capacitor becomes a wire. means an inductor will oppose high frequencies. A capacitor will allow the high frequencies to pass through. Similarly, at low frequency, it will be reverse. This will be a wire and this will be an open circuit. So we can actually use a combination of these things, to get a particular frequency. Did you guys ever think about it? How does your radio work? Think about it. You must have heard these FM channels, 93.4 FM, 95.6 FM, 100 megahertz. So the thing is, how does your device know which channel to take? First of all, if there are 10 FM channels, doesn't that mean at any point of time, all the 10 signals are being received by this thing? Just look at your phone. Your phone at this point of time is getting a signal from Vodafone, Airtel, Jio, from everything. Your Wi-Fi, your neighbor ka Wi-Fi, right? FM channels, it is getting every frequency that is present in the air. So how does your phone know that it has to take a particular Airtel ka signal only and not Vodafone ka signal? Yeah, there's a SIM inside, it will tell and all. Now, tell means what? There's not a human inside, right? You tell them and it will catch that signal and will start feeding you. Hearing it. So there is some kind of mechanism, something is happening, which will, right, tell the circuit, circuit can take only that. Yeah, phone is smart. अंश बोल रहा था स्मार्टफोन है ना स्मार्टली ले लेगा. So see what happens exactly. So inside, right, we have a coil. Let's say you have different FM channels or something. Let's say we got F1 100 megahertz. Let's say we get F2 101 megahertz. Let's say we get F3 102 megahertz and so on. Now, when you say this megahertz, what are you actually talking about? These are nothing but an electromagnetic waves. This is our next chapter, waves. So when you say an electromagnetic wave, it is nothing but a combination of electric and magnetic fields. So they have magnetic fields present inside, which is given by B naught sine kx minus omega t. We will see this in the next chapter. This is a wave equation, right? So here that omega is 2 pi f. Now, if there is a magnetic field in the region, don't you have magnetic flux? If you have flux in the region, won't you have EMF? Faraday's law. This will be B naught A omega cos kx minus omega t. That means this each of the signal is generating a respective voltage. So this is generating V1. This is generating V2. This is generating V3. That means if there are 10 signals, there are 10 AC sources on that particular coil. That means you're not getting a single current, you're getting a combination of currents. Right? And we know omega resonant is 1 by root LC. Now, if you look at this old radio, right? You ever seen that knob? When you turn that knob, we can adjust the frequency. Right? So what we do by changing capacitance, we can change the resonant frequencies. So that means what frequency you want, you can set it. So when we set C1 such that F1 becomes the resonant frequency, and what happens at resonant frequency? You generate maximum current. The current due to F1 dominates. That particular signal is converted into voice or whatever. Let me show it on a graph, you'll understand. So if I try to plot all these things on a graph, so let's say this is the current versus capacitance. So for the red one, the F1, let's say this is the graph. For the green one, this is the graph. This is the graph. Now see what happens. You are adjusting the capacitance. So when you adjust the capacitance at a particular value of C1, I becomes maximum. Now look at this point. At this point, what is the current? Red ka current is this one, green ka current is this, black ka current is this. So in the total current, how much is the red ka contribution? Almost 98, 99%. So the other signals are too small, so you will hear red ka signal. Now if you increase the capacitance, as you keep going forward, at some point green signal will come. So at capacitance C2, F2 becomes the resonant frequency. Now look at the current at this particular capacitance. Green is dominating, red and black are very small. F2 ka current will dominate in the circuit. If you keep increasing, then again you get C3. So F3 will dominate. So the thing is, there are other currents in the circuit also, but you made this particular current become maximum. And that is the reason when you're tuning this thing, sometimes you must remember in old radios. At this point, can you hear both the channels? So when you're tuning it, can't you hear both the voices sometimes mixed up? So when you put that exact capacitance, that you can hear more clearly. Is this making sense, everyone? This is what happens. This is how your phone or any device knows how to catch a particular frequency. That's why this is called as an acceptor circuit. You can catch a particular frequency. This is the whole concept behind your communication. How do you get a signal and how do you know, like, how does your phone differentiate between so many different signals? Is this clear, everyone? Next thing, quality factor. This is removed from the portion, but still better to know a little. It defines sharpness of the current frequency graph. So this is how it is defined as. This is your omega resonance. This is your I naught. So at a particular point, I naught by √2, which is your RMS, this will occur at two different frequencies. This is omega 1 and omega 2. This difference is called bandwidth. Omega 1 and omega 2 are frequencies. When current becomes equal to IRMS. Problem with these things now, they'll say they'll remove it from the portion, but they'll still ask. Mains में they might not ask. Even last year also they asked it in mains, but they gave bonus. But ठीक है, bits में तो है. Or when power is half of maximum. So this is how the quality factor Q is defined as. The omega resonance by bandwidth. So what are the use of this? Suppose if you have a high quality wave, this is high quality, you get a pretty sharp curve. Now see, what's the advantage of this? Suppose if you're using this in radio signals, when there is red, green is almost negligible. This is a high quality. Basically, the signals don't interfere with each other. Suppose if you use low quality, can you see what is happening? Even when red is there, green is still dominating. This is low quality signal. There will be a lot of interference. When you want to hear that FM channel, some other song is coming. Play with this. And how do you calculate the bandwidth? We know I is equal to V naught by root over R square omega L minus 1 by omega C whole square. Now you're saying this will be I max by root 2, which will be V naught by R root 2, because maximum current is V naught by R. When you solve this, you will get a quadratic R square omega L 1 minus omega C whole square is equal to 2R square. Simplify this, omega L minus 1 by omega C is equal to plus or minus R. This will be omega square LC plus or minus R omega C minus 1 is equal to 0. R square C square plus 4LC by 2LC. So there'll be two roots here. Your frequency can't be negative. So take one both plus RC plus root over R square C square 4LC by 2LC. This is a greater one actually. This is omega 2. Omega 1 will be minus RC plus root over R square C square 4LC by 2LC. The bandwidth delta omega will be omega 2 minus omega 1. That will come out to be R by L. That itself they can ask you find the bandwidth. Quality factor will be delta omega resonance by delta omega. Omega resonance is 1 by root LC. And this is R by L. This will be root LC by R, 1 by R. That's your quality factor, at least for a series circuit. Clear with this? So they will explain something called quality factor in the last paragraph. Clear? The last theoretical thing, choke coil. This is all the theory. Technically, this is what we will start with. All that complex number story and everything I told you, if you just ignore that, it starts from here. After AC circuits, we start from here directly. Meaning that RLC will explain basics and then we'll start from here. The problem with this thing is something the circuit changes now, people don't have a context what is happening. For mains and medical, it is okay, but I think people for advanced, you should have an idea. Anyway, phasors were not, I hope you can understand, it's not that deadly. Choke coil. A choke coil is nothing but an inductor. That's it, simple. Whenever you hear the word choke coil, don't get scared. It is simply an inductor. It is used as a voltage regulator. Ever thought about it? How does your fan speed change? When you rotate that knob, what are you exactly doing to change the speed of the fan? So you can increase the fan speed or decrease the fan speed by changing the current. If you give more current, it goes faster, and if you give less current, it goes slower. Now, how can you change current? One, you can add more resistance, but the problem, you'll generate more heat. Second, you can actually put an inductor because the impedance becomes R square plus omega square L square. So when you're rotating that knob, you're actually changing the inductance. And inductors do not dissipate energy, so you're safe. So by changing L, we can change the current magnitude without additional power dissipation. That's it. So if they say choke coil, that's what they mean. Now let's see some mains level questions, like the kind of question they'll ask. That is also important because that complex numbers thing, no, it is good and all for tough problems. Something silly comes, that complex numbers will eat your head. But anyway, this is all the theory that you need for AC. Clear with this? Definitely go through this. I know there's a lot of things and a lot of new terminologies. Impedance, that, there's this. Let's see few questions. I'll send you a sheet on this thing. So do make sure to solve, maybe not much, 20, 25 questions. I'll send you actually two sheets, one mains and one advanced. Let's see few questions of this. You will understand what I'm trying to say. Let's get this. Okay. What the first one? The frequency is less than omega resonant. Then what is this? Just now we wrote that thing. If omega is less than omega r, circuit is capacitive. That's a CT question. What about the second one? What does a voltmeter give you? RMS values. What is the relation of RMS values? V source RMS will be root over VR square RMS VL minus VC whole square RMS. This is 100. This is also 100. This is VC and this is VL and VR we don't know. This is also VRMS. Like I said, if they give you a number, it is RMS value. That will be root over VR square. VR is 200. Making sense? You should know your standard formulas for RLC series circuit. Any doubts on this? So here using complex numbers is like, getting a rocket launcher and trying to kill an ant. Put the formula and you're done. Let's see one more. I'll send you a sheet. Definitely do that 1 or 2 days. Mein. If you do that, it is taken care of. The chapter is quite easy. You can finish a 1 day. You're solving also. HCV has like 24 questions. If you're doing a booklet also, I don't think they'll have more than 50, 60. Let's see. You can try to understand, first of all, an LCR series circuit with 100 ohm resistance is connected to an AC source of 200. That is RMS value. AC source, how can it be constant? So that is RMS. Frequency is given when only capacitance is removed, the current lags. So you have an inductor and you have a resistor. This is what he's trying to say. If you remove the capacitance, you have only this thing. Go back to phasors. The inductance is removed, the current leads the voltage. Remember, in series circuit, we take current as a reference. And he's saying the voltage leads the current. So voltage must be ahead. We take the clockwise direction. This is 60 degrees. Then he's saying when inductance is removed, the voltage leads. So great. So how do we write this thing? So what is tan phi? So tan phi is XL minus XC by R. There is no XC here. So XL by R is tan phi. Next thing, L is removed. That means you only have a capacitor and a resistor. And this time he's saying again, the current leads the voltage by 60. So again, we'll always keep the current as a reference. If current is leading, what the voltage is lagging. So here tan phi, this is tan minus 60. This is XL minus XC by R. XL is not there. So we get tan 60 is also equal to XC by R. So indirectly we proved XL is equal to XC. And now if we keep all three of them in series, you have created a resonant circuit. Since it is resonance, Z is equal to R. IRMS will be VRMS by Z. IRMS is 200, Z is nothing but R, which is 100, 2 ampere. Power is nothing but I square RMS into R, which is 2 square into 100, 400 watts. Is this making sense, everyone? How did we do this? Clear? Let's see one more. They're not tough, but generally these are the questions. Always try to use the phasors. That VL, VC, VR, the diagram that I showed you. This one. They will always play with this one. Let's get this. Finish off, last one for the day. First of all, say 100 volt DC is connected across a solenoid. A current of 1 ampere flows in it. So if I just keep a solenoid with a battery, you know what happens, right? Current will keep increasing. But he's saying current is constant. That means this solenoid has some resistance. Remember, this is a DC battery. Basically, this is LR circuit. So after a long time, current I will be V by R. He's saying this is 1 ampere. So basically, he gave you indirectly resistance is 100 ohms. Or else there is another way to explain what is happening. He said solenoid, he didn't say inductor. A solenoid is simply a coil. So a coil will also have a resistance. Wire, no? Then he said, now you take this and connect it to an AC circuit. So you have to be careful what he's talking about, AC battery or DC battery. And this is also 100 volt AC. And he said current has become half ampere. So I will be VRMS by, so remember now he's talking about a current in AC and he's saying constant. So that is RMS. Z, this became half. So that means Z became, and VRMS is 100. So Z is 200. Luckily, there is only one option that we can solve. What is Z here? Z is nothing but R square plus omega square L square. There is no capacitance. R is 100. So omega square L square is equal to 300. What is omega? 2 pi F. F is 50. Solve from here, get L ka value. Clear with this? There. So next class when we catch up, we will do a few more problems, I think, but we will finish all the chapter in another half an hour, 40 minutes. Chapter is almost done. Actually, you can handle everything now, but we will do a few more easy questions for you to get used to it. And I'll send you a sheet today. So try that before Friday and come. It won't take much time. If you just sit and do, maybe it'll take a 1.5 hours. Do that much. So because the tough ones, I'm pretty sure you can handle with the phasors. These things you can see, you have to read and understand and actually put the things. So that is one. And the next class, right, we'll start off with waves also. So we are left with waves and wave optics. That is slightly bigger one. That whole thing is actually two different topics, but we are going to do it together. And then we have modern physics. Modern physics is not tough, but then again, I'm going to show you all weird ones. So it will look a little different from your chemistry, but the concepts are same as chemistry. That's it. Those are the two main topics left for advanced part. And then we have little main topics, which will finish it off. Okay, with that, we'll wrap up for the day, right? Do finish your EMI ka pending, whatever is there before Friday, because AC won't take much time, but 2-3 days we have to give for this also. Okay, those are out, stay back and ask, or else you're free to leave. So take care, stay safe. I'll see you guys on Friday, same time.